All right, let's talk about one of the wildest paradoxes in all of physics. It's an idea that could be the key to understanding how the universe is built, but it might also be the most terrifying threat imaginable.
I mean, just think about that for a second. What if the very atoms that make up you, me, this planet, what if they aren't the final form of matter? What if they're just temporary? And what if just touching the real stuff, the truly stable stuff, could kick off a chain reaction that just consumes everything? Yeah, that's the whole idea behind Strange Quark Matter, and it's earned itself a nickname straight out of a sci-fi horror movie, the Galaxy Eater. So today, we're going to figure out exactly why it has that name and whether it's a monster we should actually be worried about. To get why it's so dangerous, we first have to understand why it's so perfect. I mean, why would physicists even think up a more stable form of matter in the first place? Well, it all boils down to the tiny, fundamental building blocks of everything. You know how the protons and neutrons inside every atom are made of even smaller things called up and down quarks? Well, strange quark matter, or SQM for short, is what you might get if a third kind of quark, the strange quark, crashes the party. They'd all merge into this single, unbelievably dense soup of all three flavors. And this is where the Bodmer-Witten hypothesis kicks in. It basically says this three-quark mixture isn't just some weird, exotic possibility. It's the true ground state of matter, the lowest possible energy level. That means the matter we're made of is only metastable. You can think of it like a bowling ball sitting in a little dip on a steep hillside. It's stable for now, but all it needs is one little nudge to start rolling all the way to the bottom. So why is this state so much more stable? Imagine you squeeze matter really, really hard, like what happens inside a neutron star. The up and down quarks get packed in so tight, they have tons of energy. But if some of them can suddenly change into strange quarks, it's like opening up a whole new set of empty parking spaces in a completely full garage. The quarks can spread out, find a lower energy state, and the whole system just relaxes into something even more stable than the nucleus of an iron atom, which is pretty much the gold standard for stability. Okay, but this isn't just some theory scribbled on a blackboard, right? If this stuff is for real, we ought to be able to see it somewhere out there in the cosmos. And the best place to go looking is inside the densest places we know of, the collapsed hearts of giant stars. Turns out, these super dense stars could come in two different flavors. You've got your regular neutron star, which is held together by its own immense gravity. If you add more mass, it actually gets smaller. But a strange star? It would be held together by the strong nuclear force itself, kind of like one gigantic atomic nucleus. That means it could be way smaller and, get this, it might actually get bigger when you add more matter. It's playing by a totally different set of rules. And the differences would be really obvious if you could get up close. A strange star's surface wouldn't just fade out. It would have a razor-sharp edge. And because it holds itself together, you wouldn't need a whole star's worth of gravity. That means you could have planet-sized strange stars or even tiny little chunks of the stuff just floating around, which scientists call strangelets. And here's the kicker. We think we might have actually found one. NASA's NICR mission on the space station took a look at a pulsar, and it turned out to be surprisingly small for how heavy it was. When physicists crunched the numbers, they realized its tiny size was a much, much better fit for the models of a strange star than a regular old neutron star. It is probably the best evidence we have that this stuff really exists. Okay, so if strange matter is real and it's super stable, let's circle back to that terrifying nickname. What would actually happen if a tiny piece of it, a strangelet, ever hit the Earth? In theory, the process would be a horrifying chain reaction. A negatively charged strangelet would just pull in the positive nucleus of a nearby atom. That nucleus gets swallowed, dissolved into its quarks, and then those quarks get converted into the more stable up-down strange combo. This whole reaction releases energy and makes the strangelet bigger, hungry for the next nucleus. It would basically be an unstoppable catalyst for converting the entire planet. And the end game of this runaway conversion? Well, it's pretty chilling. The whole Earth, the mountains, the oceans, every living thing could be transformed into a perfectly smooth, super dense ball of strange matter, shrinking down to about the size of a city block. Just a silent, dense orb where our world used to be. Okay, but before you start to panic, here's the really important part. We have a massive cosmic scale safety net. You see, nature has been running this experiment for us with way more power than we could ever dream of, and the results are in. We're still here. Look,
We worry about what might happen at particle colliders like the LHC, but nature's own particle accelerators are way more extreme. For 4.5 billion years, cosmic rays with energies millions of times higher than anything we can create have been slamming into the moon. If those kinds of collisions could make dangerous strangelets, the moon would have been converted into a ball of strange matter billions of years ago. The fact that it's still up there is the best proof we have that we're safe.
And the scale of that safety margin is just ridiculous. Based on the fact that the moon is still the moon, scientists have calculated an empirical safety factor against a Strangelet disaster. It's a 1 followed by 22 zeros. That is one of the most solid safety arguments in all of science. So if it's not going to eat us, the whole story changes. Strange matter goes from being a horror story to one of the most exciting quests in physics today. The question is no longer, are we safe, but how can we finally prove this stuff exists? One of the coolest ideas is to actually listen for the song of a colliding star. See, when two of these things crash into each other, they ring like a bell, sending out ripples in spacetime called gravitational waves. Our models predict that a strange quark star would ring at a very specific, higher frequency than a neutron star. If we ever detect that unique gravitational pitch, that's it. That's the smoking gun. Unambiguous proof. And the hunt is seriously on from all angles. Our gravitational wave observatories are listening for that stellar song. Telescopes like NICER are scanning the skies for more pulsars that are too small for their own good. And up on the International Space Station, the AMS-02 experiment is literally trying to catch a stray Strangelet as it zips by. And that leaves us with one last, really profound thought. The galaxy eater threat might be basically zero, but the core idea, that's huge. Because if the Bodmer-Witten hypothesis is right, it means the very stuff we are made of isn't fundamental. It's just a phase. It suggests that the ultimate destiny of all matter in the universe is to one day, eventually, settle down into this perfect, quiet, and incredibly strange final form.